Dear all, good afternoon. Now we will start the today's session. So here with us, Professor Sudhindra Kumar K is there from PSU Bangalore. He has already taken one class with us during our online sessions, and he has given some new thoughts to our participants. So I will just feel honored to read out his biodata, and after that I will request him to start the session. So, Professor Sudhindra Kumar K received BE from BTU and holds master's and doctoral degrees from VLSI.NITRourkela. He started his career with Wipro Biomed, Bangalore. Worked with Beckman Limited Equipment. His professional career includes a stint as application engineer for Freescale Semiconductors and product test engineer for Qualcomm. He has got significant experience in SMDP2 and C2ST, so Special Manpower Development Project 2 and SMDP Chip to Systems Development Project under the aegis of Ministry of Communication and Information Technology, MIT, Government of India. He was responsible for establishing VLSI labs, training and EDA tools, chip design and tape-out. He has got more than 30 publications in reputed journals and conferences, and also a reviewer for the LCBR VLSI Integration Journal, IEEE Consumer Electronics Magazine, and IEEE Transactions of Emerging Computing Systems. Currently, he is Joint Domain Head of VLSI and Embedded Systems in Department of Electronics and Communication Engineering, PES University. So I welcome Professor Sudhindra, and I will share his PPT. He will be live with MS Team to our participant. Joy, can you please share the PPT? So this is a very interesting topic. I am also new to this. We try to learn a new thing from him today. Basically, always give many new things, so we take away to our own today. Okay.
Thanks for your kind words and introduction. I think I'm audible. Yes. Now I'm audible, right? Yeah. Okay. Thanks for your kind words and introductions. So today, actually, the digital twins, it should not be an introduction to the digital twins. It should be something like applications of digital twins or something like that, etc. But none of the means if you are using the word Internet of Things, then we should have a digital twins must be discussed, and its associated security aspects and its associated applications security aspects needs to be discussed very well. So what is this digital twins? Means for my information, how many of you know about digital twins? Heard about the digital twins? What exactly it is and all? Means anyone in the offline audience? Digital twins? If yes, please. No. In online audience, does anyone have a idea on digital twins? You can. If you have any more questions on it, you can ask me at any time. You can stop me at any time in between. So now let's go to the digital twins. So basically this again it's a part of Industry 4.0. Again, it's a basically Industry 4.0 concept. That is, it's a digital twin is a representation of an entity, including its attributes and behavior sufficient to meet the requirements of the set of use cases. The case is if I have a car in mind, if any, okay, let's take any Mercedes-Benz or a Maruti Suzuki or produces a car, you will just equal it to my car, you will just create another car. It is virtual car. Means its engine, its brake system, its seat belt, its mechanical system, everything will be co-created. Means it will be not co-created, virtually created actually. Virtually created. If you have a car, a physical car, then you have your car's equivalent virtual car will be available. Virtual car will be available. Means what and all is happening on your car naturally it will be reflected on your virtual car also. Virtual car also. For example, if we go creating a car, it's a dream for even every automotive company itself. Creating a complete virtual car or a complete digital a physical car. But now most of the cases like generators, motors are already created, and also lathe machines or CNC machines and smart machines where we use in the smart manufacturing, etc. and all. Smart manufacturing, etc. and all these equipments are already created. I don't think creating a virtual model of a generator is impossible in today's modeling tools. Like for example, it may be using Python with a lot of other tools, or they're both mechanical, physical, and electrical. All parameters can be added, and it can be a virtual model of a generator can be created. A virtual model of a motor can be created, electric motor can be created. In the same way, a lathe can be created, or any other manufacturing equipment can be created, a virtual model can be created. In the same way, a virtual model of a car can be created. So this is where exactly the digital twin is. One, we have one clone, we have a physical thing. Another one, exactly the same physical what we have a same virtual model. Means it's what's there new in this. It's not, there is nothing new in this. Creating a virtual models, experimenting on virtual models is a very old idea, and again the people keep doing it. But here, in real time it will get updated. In real time it will get updated. Means, for example, if I'm a generator malfunctions, virtual machine also malfunctions in the cloud. A virtual machine where it is saved in the cloud. It will be in real time. It will be mimicking the real generator, real motor. Means, for example, any motor manufacturer manufactures a motor or an electric generator. For every electric generator and every electric motor, for example, let's take, I'm not advertising anybody here. For example, if you have a Mahindra generators and Mahindra motors, for every generator and motor the Mahindra produces, you will create a one virtual model for every model is. If I buy one generator from that, you will get a virtual ID for that. The cloud that this machine's virtual machine is there in the cloud. If how it works. And again, it will be working in the real time in the same way. If it finds a problem here, there also it finds a problem. So it's a twin actually, it's a digital twin running parallelly with it. If I want to update, for example, I will stop this. I will stop this. I will stop this. Yeah, I will stop this. Go online. I will stop the generator, but I can I can put the digital twin mode in one small off mode. I can put the twin in the off mode. I can switch off the generator, physical generator. I will switch off the physical generator. After switching off the physical generator, I will apply the software update on the generator on the virtual machine. I will update the virtual machine. I will update the virtual machine, and I will switch off the physical model. I will update the virtual machine, and I will run it for half an hour. I will see that the update really makes sense or not, whether the update really creates any problem or not. Then gradually, once the update is ready, then again it starts running. Then again, after virtual machine is running, slowly the virtual machine itself will find that update not installed on the actual machine. Then through over the wire, the virtual machine by itself it will send the data to the original physical machine, and it will update the software on the run. On the run, or stopping the operation for some time, it will update the software. Means your installation of the update is not on the actual machine, on the physical machine. All your updates, upgrades, software manipulation. Initially, you have to debug it. Machine is wrong. The maintenance engineer, if he is a maintenance engineer, if something goes wrong in the field, if the generator goes wrong, the engineer does not run to the physical device. He will just open the virtual machine, run the open virtual machine, You will find out what is happening in the virtual machine. Slowly you will see whether the software update is possible. You will update here, then again, gradually I will ask him to start the machine. Slowly it will get updated over the wire, through the internet, and again it will get updated. So gradually this is a twin model of another exactly the virtual model, the twin model. It's a twins, just like our physical twins will be having the same face, same characteristics in the initial days of birth. The same way, the same case here, a virtual machine will have, or the cloud will have a twin equivalent of the actual machine in the physical world. So this is where exactly the digital twin is there. But now, just a few months before in October, I attended one conference called the IES, Indian Semiconductor and Electronics Association's some Vision Summit 2022 in Bangalore. The case, the 2 days, many companies presented their case. Means from all 5 verticals of a semiconductor engineering presented their cases. That is automotive electronics, consumer electronics, communication networking, biomedical and medical electronics, military hardware. Everyone speak about, almost barring few, some companies connected with military hardware. All these people, major automotive, communication networking, consumer electronics, medical electronics, and industrial control people, especially the industrial control people and industrial control and automotive electronics people. Everywhere they spoke about the digital twins. They said that in next 2 years, in few years, the digital twins will be there for every mission, every equipment, every electronic equipment you would, if possible. And also when it comes to the industry 4.0, especially as I said mentioned in my last lecture, that is taxonomy of different IoTs, that is industrial IoT, consumer IoT, community IoT, consumer IoT, community IoT, industrial IoT. What is the other IoT one I just mentioned in my last online lecture? I don't remember. So on all these IoTs, we will have one digital twin for every system, whatever we are deploying in this. And especially it is true with respect to the industrial IoT and automotive IoT. Industrial IoT, where we have our smart factories are coming up, and smart autonomous cars, smart cars are coming up. Digital twins is a necessary and mandatory technology that is going to getting deployed and adopted in next 2 years or 3 years for every car manufacturer that is in automotive and in smart factory or industrial control. So that's the reason why we have I felt that it is incomplete to have a Internet of Things. If having Internet of Things in the title of an FDP without discussing about something called as a digital twins. So in this context, the entity is the definition of a digital representation. It's typically an asset, process, or a system. Means it's a model, a generator model physically there. Exactly the generator is there is a cloud. Virtual model of the cloud is there. So the digital twin information includes, but these are somewhat mandatory components, but you can add a lot of things like physics-based models and data, analytical models and data, time series data and historians, transactional data, master data, visual models and all computations, all these things are clubbed together, needs to be molded. For example, for generator, we may not need time series data and all may not be required. Historians may not be required for the generator. For some other lathe machine or some other equipment, injection molding machine in a smart factory may need a time series data. We don't know. Based on that, means I'm not going deep into any technology or digital twins deep technology, and I'm not going in. The reason is the crowd in network crowd. Some may understand, some may not understand. So there are a lot of things like some transactions. These are all we know. What is the physics-based data, analytics data, time series data? These are the 3 important. Out of these 3 data, 2 at least are there. 2 data are almost there in everywhere. Transactional data, master data, visual models will be used in this one. So this is how exactly the digital twin comprises of a data computational models and service interfaces such as object in an object-oriented programming language, whereas a member data methods, etc. Programming, Python-based programming can be used to build the digital twins. See, basically here we have the basically, we have here the design, production, operation, business. Here, what exactly happens is principal data visualization here. It will have a descriptive, diagnostic, predictive, descriptive visualization, and augmented reality. Everything will be modeled into your equipment base. So this basically this equipment is just showing an aero engineer. But actually, in the design, we have a spec models, process, production, human machine interface, operation. And again, data will have statistics, machine learning, artificial intelligence, augmented reality. This is one design, just a model of this one. What is the digital twins? So slowly we will see what exactly the digital twins, what exactly it contains. A digital twin contains data about a real world object that are required by the models to represent and understand the states and behaviors of the object. So it will have a models, process, design models, production models, engineering data in that the design side. And again, in the production phase, it will have a materials, parts, operation phase, inventory data, what is in stock, what is the production, etc., what is the status of the machine, etc. And models, we have that's a digital twin. This is basically very quite important client managed data. The models means the digital twin contains a computational or analytic models that are required to describe, understand, and predict the real world objects and operational states and behaviors. Means basically here we use a machine learning models basically as and when required. Number one. Or else number two, we can use many other models like statistical models and that. I don't want to use a statistical model. I don't want to use a statistical model. Then I can use some very normal models that Bayesian models which we use in normal modeling philosophy. Our modeling starts with what? Our modeling starts with the linear equations. From linear equations, we will go to the complex calculus. Then complex calculus 2, we will go to the next level, Bayesian networks. Again, we will go to the next aspects, and so in the same way we teach out something called the statistical reference models and all. Generally, the people feel that machine learning model they will make out, but most of the machine learning models does not work for the real-time connection because of the machine learning itself. It takes a too much amount of time. Generally, we use the statistical reference models to build the equivalent twin of my car, equivalent twin of my generator, equivalent twin of my lathe machine or some equipment in the factory, in the smart factory. The digital twin contains a computational or analytic models that are required to describe, understand, and predict the real-world objects and operational behaviors. Generally, statistical reference models are used. The models may include the basic based on physics or chemistry, engineering or simulation models, data models, statistics, and artificial intelligence. Means it's not related. To the best of my knowledge, till today, the statistical reference models are widely used. But in future, it may include machine learning and artificial intelligence based digital twins are also possible. It may include the 3D models and augmented reality models for aiding human understanding of the operational states and behaviors of the real world. The case is it's not only the generator motor, what the example we are doing there. A complete system, for example, a complete factory, I may make it as a virtual factory. Building one by one step. For example, today I have one smart factory here producing some plastic bottles or something, or plastic bottles or something like etc. So every equipment here, I will just get a model into the cloud. Slowly, my complete factory will be there. My complete factory will be there inside the cloud. So the factory and real factory will be there in the physical world, and the full factory will be there on the cloud. The full factory is there on the cloud. Then again, you are running a factory paralleling with physical factory running. There you understand the problems and all, update there and again check whether it works or not. Then again you start the factory, real physical factory and all. So it's there when it goes to the from vision small individual component we may have in a statistical reference models. Once we go up to the higher level factory model or interface between the two missions, talking between the two statistical reference models and optimizing that communication, all where exactly again our machine learning and artificial intelligence comes into the picture. Decision making, wherever there is some learning aspect is there. Especially in modeling a generator, in modeling a motor, as such, there is no much learning aspect. The statistical modeling can work. But when it comes to the total factory, running a factory, talking the communication and engagement between the several methods needs some intelligence and learning where exactly where it goes large scale. From a small scale generator motor, I may not need a machine learning. Once we go for the factory level, I need a machine learning and artificial intelligence in this. The next, the services. These are the three important components what we mentioned. That is the data and models. Data is required. A minimum amount of data for statistical reference, building a statistical reference model. The data is required, records is required. Then again, models we know. And service. A digital twin contains a set of service interfaces for industrial applications or digital twins to access its data and invoke its capabilities. The common approach, we can construct a digital twin for an equipment for its constrained digital twins. A production line digital twin from the constrained equipment digital twin. A factory digital twin from its production line constraint. See here we are just mentioning. The common approach is to construct a digital twin for an equipment from its constrained equipment. A production line digital twin can be molded from a constrained equipment in the factory line. A factory digital twin from its production line. Like just a component can be made, a conveyor belt or a complete factory can be built as a digital twin. Relying on the digital representation enabled by the digital twin, we can enable a host of smart industrial applications to run operations in the real world, optimally improving the operations. Means this is where exactly means that I may be talking at a very high level, very theoretical level. If you ask somebody a deep questions for me, 100% I don't know the answer, number one. And even many experts doesn't know the answer because digital twins, no practical digital twin means there is no practical digital twin working in real world factory. Means in any of the USA in small experiments are there. Some pilot projects or proof of concept projects are there. But everybody speaks about the digital twins, some and academic research and again industrial research needs to be happened to create a virtual factory in the cloud. So that it's a digital twin equivalent of a factory must be there. So that I feel that the crowd here is heterogeneous. May not be everybody may not be a faculty student, a practicing engineer, researcher, PhD student. Our crowd is there. I'm just keeping this topic open to almost everyone. I may not be focusing on the electronics engineer or software engineer or AI/ML engineer or not something like that. A digital twin where everyone has to be taken, means everyone has to take it seriously because the next 3-4 years the digital twin will be reality without doubt. So if you have a car, the car will be there, a virtual car, and you will be knowing what virtual car is doing. Stop your car, just check the data in your virtual car. What is the data? There you can see, here you may not be able to measure your temperature of an engine oil, or else what is the brake system has jammed, whether there is a proper lubrication in the transmission line or not. All these things you cannot measure on the real car on your own. But in the virtual machine, open your virtual machine in your mobile phone and see what is that. It is exactly what maybe 10 minutes before data will be there on the 10 minutes data, 15 minutes old data of oil temperature, this lubrication level of a transmission, then all these things will be there in your mobile phone. Just 10 minutes old data will be there on your virtual car. So this is where exactly, I hope you understood what I am saying, right? So on your virtual machine, you can open it and see what are the values, typical values and all. So if this is the case, you push it, means, and then again, how do you implement this? How do you implement? What are the platforms to implement this? How do we start the research for this? What is the cutting edge research in this area? All these things we will discuss. So this is, I hope I tried my level best to make you to understand what is basically a digital twin and why it is important, why everybody is focusing on this. The simple thing is, if a digital twin is there, then you may need to pay less insurance because everyday data of your car is available, logs are available. You can ask the insurance guy that see the log, see the data, you charge me less insurance because my car is good. My car is good. So this is all the one side of approach. Already this has started in one of the other way in the most of our markets, especially in the car insurance market. But okay, let's come back to this basic functional components of a digital twins. We already discussed the data and model. Now we'll look at the service. So relying on a digital representation enabled by the digital twin, we can enable a host of a smart industrial applications to operations in the real world, optimally improving the operations. So this is basically this is the see here. This is actual industrial application. This will be the I think. So this is the real world. We have a real world of applications. Whether we have a digital twin, then there is an applications running on the cloud. So the topmost layer is the cloud where my applications are running. Based on the applications, what are the output will come because the industrial applications will crunch a large amount of data. Large amount of data means it will take a data from all the factory, production, etc. and it will crunch the data and it will give some input to the digital twin. The virtual, there is a digital twin means it's a virtual one, the middle one. There it will work out what, okay, new input is coming from the app. Based on that input, let's run it on a virtual machine, virtual twin. So let us see what is the problem. If no problem, then do it on the real one. Simply, you are running a cloud, you have a cloud data, and an industrial app, whatever I'm showing here, the topmost layer, is a software layer. Basically, it's a software layer running on the cloud, which crunches large amount of data. Crunches large amount of data means, for example, let's take there is a factory which is producing a Coca-Cola bottling plant, or else let's take one smart city network which is collecting a large amount of data from the city or something like that. So it is collecting a large amount of data. The large amount of data needs to be crunched, plotted, planned, analyzed, then some inference needs to be drawn. After drawing an inference from the data, some action needs to be taken. That action will be taken if it is taken in the real world. We don't know what are the consequences, whether the system will fail, whether the system will go faulty, whether system will, what happens to the system we don't know. We don't know. So for that reason, what we'll do is we'll run it as a virtual twin. Large data came and we crunched it, we got some meaningful information. Based on the information from the industrial app, we have to take an action now. I am not daring enough to take it on the real world factory. I will take the decision on the digital twin, virtual twin, which is there. Then I will run that. Based on that data, I will take a control action in the virtual factory. If there is any dangerous is there, then no need. I will take that. I have a chance to control. I have a chance of control set. Take it. So in the case of a real world, that chance is not there. And once you run the real world machines, then again it's gone. There is no option for control set. In virtual machine, you have an option for control set for the new control action, but you are taken based on the industrial app inputs. So this is where exactly the safety plays important role. The safety plays an important role. Your production does not stop. You have a better predictive maintenance. Predictive maintenance is there. Then again, you have something in control that I want to experiment something, but I don't know how to experiment on the real factory. I will run it on a virtual factory and I will see what happens. The virtual factory is the digital. For virtual factory case, everything will have a virtual in future. Next 2 years, even a small pen manufacturing factory will have a virtual twin of it. Even the car, every car will have a virtual twin. If I buy a car, they will give an access to a virtual car in the virtual. Every car will have a virtual car associated with it. So you can imagine every equipment, every machine, your motor generator, whatever the motor generators we use today, motor for pumping the water to the water tank, everything will have a virtual machine, virtual twin in the cloud. The relationship among the digital twins and systems. The levels of abstraction of digital twin is such that it is sufficient for the requirements for the specific application or use case. A discrete digital twin is a single entity that provides value without needing to broken down further. Assembling discrete digital twins to create a composite digital twin is figure as vertical expansion that describes the increase in composition from single to many entities. So here this is how exactly we can do. So this can be the, so here we have a discrete digital twin or a single atomic entity. From there we have a composite digital twin. We can build a many digital twins. And again from that we can have a further system or assembly of digital twins. Means it looks complicated for me. Then what exactly how to understand this? The case here is simple. For example, my generator is there. I have a, let's say I'm using some Mahindra company, some particular model generator or motor I am using. For my case, I have a one digital twin is there. That is a single entity or an atomic entity. My home, my motor, my digital. But there may be a lakhs of customers who have bought the same model, same custom, same thing. For them, it's at the starting point, it's the same digital twin. If it is a new motor, the digital twin remains same for everyone. So then, but based on the usage, based on the how we use, the digital twin will have a different color, even though we have a different motor, the same motor. I may use it for 1 hour, somebody use it for only 15 minutes, somebody use it for field also, you will use the same motor to fill the to water the field, etc. So there will have a different composites of, even though it's the same product, will have a different composite. Composite digital twin will get created. That who the customer, the Mahindra company will do that composite component because he has to address lakhs of thousands of people who have bought the motor, same motor. He will club together and he will see what is happening in the overall this product lifeline. And he will take a call on it. So the digital twin at the individual level, it's a single entity. For me, it's a car. My car and a virtual my twin. But Maruti Suzuki, in that model, thousands of cars. How many cars they have sold? For every engine, for every twin, they will all club together and they will see that is a single twin. What is happening in the overall this product? How they are doing? Which part is coming repair for long frequently? Which is unstable part? Which is what is the mileage? What is the average mileage? What is the lowest mileage? Why the particular twin is giving my lowest mileage? Every data will be available at the every evening. The product manager and Maruti Suzuki will have a data. What are the problems of today? How the twin worked. So this is how we can build a composite models of from each digital block when the companies will build a large digital twins. Or further, I can say the composite digital twins means many colors of digital twins may be there for a single product. So as the scale and scope of a composite digital twin increase, it may expand horizontally from a composite assembly to a more complex system. So there can be an hierarchical, there can be associational, there can be a peer-to-peer. So these are the different hierarchical is a component, the equipment, the production line. There is a how the digital twins can be built in a hierarchical way. In the association, assembly means it's a production line. Peer-to-peer means it's individual component. Peer-to-peer means each we cannot be clubbed together. It cannot be a clubbed together. But here peer-to-peer generator example, I can make it like this. I can build a large digital model, but again there may be something a solar type of equipment, or else there can be an equipment where the weight of one entity may not be possible in the other entity. The clubbing is meaningless. For example, a medical variables. In medical variables case, if I have some sensors in the shoe, right? Adding a data is meaningful because weight of a person, behavior of a person, everything is completely different. The medical variable people are not going into the digital twins at all. They are not investing in digital twins. The two major people who are investing in digital twins are industrial control, factory automation. Another one is automotive vehicles. Automotive suppliers and the industrial control and factory automation people are investing in this digital twins, not the medical people. In medical people, they cannot build a composite or hierarchical assembly of digital twins or associational assembly of digital twins.
The competition time will be also high.
Very high. It's not.
Because then some healthcare like application are time sensitive.
Exactly.
So it's not useful.
Exactly.
That I was thinking about.
Exactly. That time sensitive also. They're not at all investing in it. They're not thinking about it. That's it. That is not our case. We have happy with our individuals having this one. We talk to the individual, whoever wears, if you have a problem, we'll talk individually. There is no meaning in clubbing the disturbance like this and disturbance like this and. So that is where exactly the peer-to-peer also they can. So this is a basic entity cycle. So the disturbance is a solution to the information silo problem. The information about an entity is usually scattered across multiple information sources, which are developed and maintained by different organizations. The figure shows how the disturbance can be used to tackle the information silo problem. So the case is here, there is a digital world and a physical world. The manufacturer side, the customer side, the system. Here we have a product type, then product instance is created in the virtual. And again, we can build the product type instance and product type instance system context in the system context. So total life cycle information can be collected in the digital. Many of the information silo problems can be addressed by offering a single entry point access to the life cycle information of entities and maintaining relationship among the information in one district twin across the multiple district twins. So this is a common technical aspect generally discussed in this one, like information modeling, security, population, synchronization, connectivity, deployment. Everywhere it is there. In digital twins are also there. So the next technical aspects, what is this information modeling? What are exactly we will do here is the core part of the digital twin is information which is related to the different life cycle phases of the underlying entity. Information population means information for digital twins originate from sources. Some have maintained inside the digital twin. Synchronization, again the digital twins interact with each other components to facilitate the interactions. We need to have some KPI like interface needs to be built. Then connectivity is 4G, 5G, we can imagine that part. Deployment is, we need a cloud basically. Without cloud, digital twins cannot be deployed. Cloud is a mandatory stuff, anything to do with the digital cloud, in digital case. Then again, the basic thing is today the cloud-based solutions. For example, most of the cloud-based solutions today, especially in the area of the Internet of Things and the cloud-based solutions. These are not, actually the problem with this cloud-based thing is they don't have a backup. We feel that cloud में backup है, but cloud का backup क्या है? We are not bothered because we believe and we 100% believe in Amazon, Microsoft, Google and all. But somehow they will retrieve the data, maybe 10 minutes late or maybe 20 minutes late. But they have to think that confidence the customer they have to maintain. They have to ensure that something they have to do. So basically the cloud-based systems, again, now see the cloud-based systems initially it was a storage. Basically the storage area networks was there last 15 years back. The subject was also there in the computer science called the storage area network. Now it is an obsolete with the advent of the cloud. The clouds, now the clouds were initially was known only for storing the data. Now the cloud became a place where we do computing nodes. And again, we keep FPGAs in the cloud. From my local Vivado software installed on my laptop, I will dump my code into the FPGA. I will see the output, then I will give back the FPGA. FPGA I can take it for rent for half an hour and I can deploy the code and again I can check it and I can come back. Means for example, Intel OpenVINO. Means you can check it out. Intel, there is one thing called the OpenVINO platform where I can use FPGAs, Intel FPGAs for free of cost. Any academic institution can use it for free of cost. So this is where what exactly, for example, if you use any NVIDIA TPUs, you feel they're available for rent, or also for academic institutions is available for this one. So we can directly use it. So computation is one, storage is over, computation is over. The next level is the digital twin, where exactly we are running a system. Storage, computation, already done. NVIDIA, we have access to the GPUs, TPUs and all. Storage already we are storing and retrieving. The third part is the district twin means that we are increasing the cloud. We are getting the cloud to the next level. It is cloud infrastructure to the next level. That not only the storage, not only the computation, we are running a complete mission, complete system. I'm running a factory on the cloud. I'm running my complete equipment on the cloud. Virtual model of my generator is on the cloud. So means I have a factory on my cloud basically. That's what that needs to, that is an understanding. That is an understanding what should have made. Cloud platforms, not only the store and compute, they will hold my complete virtual factory. It will include generator, conveyor, like production, what is happening here, what changes are happening in the factory. In real time, that virtual machine is also just have a complete real world connection. They are running in synchronously. I'm running a factory on the cloud. That's where exactly the cloud needs to be updated. The cloud needs to be updated. The cloud is a district twins is an Internet of Things problem, but basically it's a cloud problem. It's basically a cloud problem. All the cloud computing and the memories and the memory and computational requirements of running a factory there on the cloud is a cloud computing research problem, open research problem. It's an open research problem. So apart from this, now I will come to the ECE part of this. ECE, electronics of engineering part of this. How do you provide a infrastructure, computing infrastructure to such a huge system to run a digital twin on a cloud? Again, you need a very high performance systems, very high performance chips, very high performance FPGAs, etc. etc. Even today, we have a large motherboards in clouds running FPGA boards. Means I have seen a cloud centers with 64 cloud centers with motherboards with 64 FPGAs, 128 FPGAs on them. Each time they will be dumped with a reconfigured with a new architecture for sorting, for merging, joining, and all data joining. Basically, it will be running at a so fast rate, it will give the customer data within some minimum latency. So the problem is there at that level that needs to be addressed, which I mentioned now. The interoperability, data interoperability, control interoperability is a common problem at once. Then again, the application areas of digital twins is basically in the design we have, manufacturing, maintenance, and implement. Basically, the first one is very limited. Even still, the people say people give one or two examples. There are no much in the design side, but manufacturing, maintenance, and resource utilization, the digital twins really make sense at present. Whatever we discussion. The next, see, there are more details into the digital twins now. It's not going to it's a slide notes. Actually, slide should not be made in such a way. Just for the benefit of the participants, I just made a notes in a very bad shape. But here we can have a see here. Generally, what exactly the digital twin contains is at the system level, at the design level, it will contain a predict. What and all we have to make is in models we have predictive model, prescriptive model, and descriptive model. All three will come. Means predictive model, prescriptive model will have a configuration settings, system models, and adaptation requirements. Then again, descriptive model will have a domain model, conceptual model, product model, configuration model. Predictive model will have run the simulation models, and it will take the analysis from the descriptive model and give a decision to the prescriptive. Take the data from the descriptive model. Call it predictive model will take a decision, and again it will give the data to the prescriptive model, so that it will change the configuration, settings, systems, and all that will get deployed in the real system. From the real system, we will get a monitoring. Then it will a digital shadow of data will be created here. Digital shadow. From the digital shadow, the input will be given to the descriptive model. Descriptive model supplied to the predictive model. Predictive model will take a decision. Then decision will be given to the prescriptive model. Prescriptive model will give a prescription to the actual real world system. This is exactly how the digital twins can be designed. How do you design a digital twin? This is how we can design a digital twin. That is, in the models part, data part, and actual system part. Data we'll get from the real system. Then again, we'll run these three models appropriately, and we will get the done job. The next is the same thing. Again, in the case of a manufacturing, what data we will get? Waiting time. In the design data, what we will get? We will get a process data, technical data, data constraints, year model design, product design, all this. When it comes to the manufacturing, how do you design this? Digital twin, the same product, same thing. You have a predictive model, prescriptive model, descriptive model. These three models you have to think. Generally, what happens in the descriptive model? Generally we will have a UML models. I think UML, Rhapsody, and all you may be knowing. You might have heard about these tools, the UML, Rhapsody, and all. Generally, in the descriptive model, we will have a Rhapsody model because it's a data flow model basically. In predictive model, we basically use linear equations, linear algebra, some system theory equations will come. In prescriptive model, it's basically again the UML Rhapsody models will come. But in the predictive model, if you take at the basic level, it may be a linear equation. At the above level, it may be a predictive equations. At the above level, statistical reference models. Then machine learning models will come into the predictive model. The most complicated model in the digital twin is a predictive model where the decision making happens. That in the decision analysis will be given, data will be given, and predictive model is the analysis part where exactly we have. In that case, in the predictive model itself, we have a confusion what needs to be used. What needs to be used? That is, what needs to be used means, for example, there is a statistical reference model, a linear model, statistical reference model, or a machine learning, or AI model. Which one to use is still a big question in the predictive model. But more or less a prescriptive model or descriptive model or a computer science based methods, modeling methods where the data flow modeling, Rhapsody, UML, Python can be used to model the prescriptive model and descriptive model. So the predictive model is a complicated thing stuff, either way in building stuff. The case is this is in manufacturing what we will see, waiting time, resource usage, product quality, measurements. And we will see again this type of components in production or manufacturing. In the case of a maintenance, what we will see position, energy consumption, environmental data, user operation, material quality, failures in the maintenance. Accordingly, a digital model for maintenance also can be created using same prescriptive models, descriptive model, and the predictive model. The component we see is different. Here we will see the energy consumption, environment data, position, status, material quality. In the case of a manufacturing, we will see waiting time, resource utilization, measurements again. In design, we will see a different thing like constraints, technical data, environmental data, etc. The big question is here. Fine, the concept should be fine, everything is fine, virtual model is fine, everything is fine. But what is the computational requirement of running a virtual model? What exactly we need? The question is what exactly we need. Then we can make it. Okay, the final one is let me come back to that. After maintenance, we have utilization stuff. In the utilization model of a digital twin, we look out for location, psychology, behavior, environmental data, psychology, etc., labor, etc. We will see the utilization. Looking ahead, what are the things we are looking ahead in the case of digital twins? And what is looking ahead is, let me read out because this need is quite important. The identification and description of the presented architectures of DT applications based on the conceptual modeling framework characterizes the current state of art in digital twins, especially the industry 4.0 needs. It provides a language to speak and discuss about digital twins, especially from software engineering perspective. But in other perspective, is very important. Only software cannot build digital twins. Only software cannot build digital twins. In addition, it allows reuse concepts using digital twins because many DTs are hybrid architectures. Mix of variants. It's a mechanical, electrical, and optical. Lot of things are there in the factories, but everything needs to be embedded in a model. The easiest way is software, which we have described now. But to run that software, we need an efficient hardware. That is basically the requirement. And also we need a low power hardware. That is the another biggest problem in the today's data center business is electricity bill. Another one is AC bill, means air conditioned maintenance. For example, you can see in Amazon center in Bangalore, you can see every day there will be a lorry of ACs going in, lorries of ACs. I'm literally speaking air conditioning equipment actually. Air conditioning equipment.
Energy consumption.
Energy consumption, okay, energy consumption is also fine, they're ready to pay the bills. Electricity bill, we have to pay, we will pay, no problem, but the problem is the heat it is generating, and again, how much it is destroying the servers. The amount of heat generating, it destroys ACs, it destroys the motherboard, it destroys the amount of heat generated. The most of the, when I see the initial data centers in 2014 or 2012, not 14, 2014 I was here. 2012, when I see the data center for the first time, the PCBs are normal PCBs. And again, today, if I see 2022, when I see the Amazon data center very recently, all PCBs are water-cooled PCBs. Water-cooled PCBs means inside the PCB there will be small water pipes, and the water will be cold water will be pumped into all the PCBs, and again it will get cooled. Again, hot water will be coming out of PCBs. So they are all not air-cooled PCBs; they are all water-cooled PCBs. Even with water-cooled PCBs, the energy consumption, not energy generation, what the heat generation is uncontrollable. ACs are going bad, motherboards will go bad. They are not able to sustain the heat. So what is the issue is because they are all using FPGAs. FPGAs are not designed for low power. Most of the FPGAs are designed for high performance, not designed for low power in general. So we have to get the low power ASICs. Means we have to generate. We have to give ICs which sit on a processor which sits on the motherboard, which consumes less power, so that less heat is generated. So that is one other part of the story. But here exactly what hardware we need. For example, we have the most powerful processor of chip architecture we have is Xenon D. Xenon D from the Intel, it has got a 128 cores. It's not octa core, it's not quad core, it's not octa core, it's a 128 core microprocessor or chipset. My 128 core chipset, we have 4 128 cores processor on a single motherboard. One motherboard with 4 Xenon Ds is a common configuration in the data center. Like that, we will have hundreds of machines. With one motherboard will have 4 Xenon Ds. One Xenon D will have 128 microprocessors, 128 cores. Like that, we have hundreds of machines in the data center. With this, it is unsustainable. Then what hardware we need to run the system? That's the one question. That's where the chip designers or computer designers needs to be thought about. The mature DTs will have certainly the elements of self-adaptiveness in combination with machine learning, simulation, and data processing element. A mature DTs can be classified as something called the map-K systems, which even I have no greater idea on that. So they require a new architectural styles to combine models, etc. So the more research or literature needs to be done to identify other architectural patterns, combinations of these patterns, which will be documented in pattern catalog or TTs. Also explicitly defining the interface to communicate with the data, and different models would support the deployment of the generic services to be used in DTs with something called as a new simulators are coming with some feature called the functional markup interface standard. This functional markup interface standard is basically meant for creating a disturbance in the cloud. Basically, most of the tools or most of the IDEs, programming languages are updating for virtual machine creation. That's what we see. We have a lot of virtuality now, augmented reality, etc. All these things are getting upgraded. Means these things are getting upgraded. Finally, the conceptual elements have to be mapped to concentrate technologies, which would allow deploy DPs on dedicated platforms with high automation. The basic thing is we don't have an hardware to run a digital twin or artifact. The suitable hardware needs to be developed, and again that's an under process. It is under process. The case now is who will if you have any questions I will take before taking a break. Any questions from the audience, both online and offline?
Sir, if we try to store data in blockchain from industrial outing by using FPGA, then we are storing data in FPGA or through FPGA in blockchain.
Okay. For example, my data is my FPGA is not in my hardware team.
Yes.
My FPGA is there in the cloud. Right? I hope I understood your question. I will commit one bit stream. If I commit one bit stream, I can have a control on which bit stream can go on right on. My bit stream is secure. Means I don't see when I'm accessing my laptop is here, my table, and but my FPGA is on the cloud. If I send my bit stream, if I have a blockchain network, I have to commit the bit stream. Once I commit the bit stream, the encrypted bit stream will go and it will get decrypted there on the cloud. It will get configured on the FPGA, and from there I will get the GUI scene on my laptop. See the waveforms, I can debug, etc. But once I commit my bit stream, nobody can change it. I hope I did not get your question. Yeah. Please repeat.
So, like if we connect the hardware like FPGA from the industrial IoT.
I will connect a FPGA from the industrial IoT.
Yeah. And I want to store data from industrial IoT to blockchain.
Industrial IoT to blockchain, I want to store the data.
Then how can we secure the data through hardware security?
Okay, fine. See, there are a few ways actually. One, whether you need to in FPGA, whether you want to implement the encryption, decryption, that part you are asking.
Yes.
So, for example, better don't implement a decryption on FPGA because already AES decryption is available on every FPGA. AES decryption is by default it is available everywhere. You use the AES decryption which is available on FPGA. And basically encryption you don't want to implement it on an hardware. If really required, you implement the decryption based on the NSX. You cannot have both hardware encryption and hardware decryption on FPGA. That's misuse of the utilization of resources and time. Resources basically, not time. So basically, if I am encrypting, if I am putting a data from my laptop, then I will use the encryption. Don't do it on IoT. Then again, if you are decrypting, you decrypt there because decryption is already available. If you have an encrypting equipment here, you don't have a laptop yet, do encryption. Then don't do the decryption. You know there is no need to have both encryption and decryption at the same time at the same place. You have to design in such a way that encryption and decryption should not occur at the same place in the Internet of Things to avoid security issues. Encryption and decryption should not happen at the same device. Then that is vulnerable to the attacks. That is vulnerable to attack. So if you are transferring the data from edge to the cloud, do the encryption and send it to the cloud. In cloud, you may have a decryption. In cloud, you may have a decryption. Or else if it is a reverse, then do the encryption and do the decryption. The edge node. So based on the application, based on the requirement, we can design design the requirement. But the case is the important thing is, the most important thing is don't keep the both encryption and decryption on the same device because keys will come.
Yes.
That is vulnerable to attacks. That is vulnerable to attacks. That's what generally the people do. I mean, I don't know about research works in academia, but in real-time implementations, in real-world companies, what I see in most of the companies is where it's not only particular to the FPGA, it's also particular to the generally any IoT system. That if it is an IoT that very well connected system, we do not do encryption and decryption at the same place. We do the encryption at the edge, decryption at the cloud, encryption at the cloud, decryption at the edge.
Sir, as we discussed, we cannot use the digital twin in medical application for emergency purpose.
Not only emergency purpose, the requirements are not up to that. Requirements are not mature.
It is possible to track any chronic diseases with this digital twin application.
That already they are doing. That already they are doing at an individual level. See, the medical data are medical variables or consumer variables or individualistic variables. Highly personally sensitive. I mean, generally what happens is, even after normalization, I want to use it, that data means also the customer would. Don't use it anywhere, just keep the data in the cloud and give it to me. When I want to erase, I will erase it completely. And again, doing a medical cloud means doing a complete medical cloud or etc. and all, it's not permitted by any, there are a lot of hacks actually. Very recently, Government of India also bought a Data Protection Act few days back, 15 days back.
Yes.
Such type of acts are already there in Europe from last 5 years or 10 years. In USA, at least from 2009. So the crunching of data, normalizing of medical personal data is a crime, is an offense. So the building a digital twins of a large scale for medical data is not permitted. And is also not required. Individual does not like it. And there is no customer requirement also. Only the hospital people like it because they want some research, especially not even a clinical doctors, but non-clinical doctors who work in epidemiology, etc. And they are interested in this crunching this large scale. Further, the different channels are.
For industrial IoT, is computing model now, it's very popular.
Sir.
So can we think about digital twins in edge computing?
Digital twins in edge computing, yes. I mean, some portion of computing that is required for the digital twin will happen at the edge computing level. See, in the edge computing, except predictive maintenance, predictive side of the structure.
Yes, predictive. That
Predictive side does not have prescriptive
prescriptive and
prescriptive or
descriptive.
descriptive also data handling is difficult, but prescriptive processing, right, happens in the edge. Prescriptive processing is the what is the most attractive place to do the prescriptive action.
Yes.
We'll take a break for 5 minutes, and if you have any questions from the online, we can take the online questions, and we can take a break for 5 minutes.
So any question from online audience? Mic is on, you can unmute yourself and ask. Or else we'll take a 5 minutes break, and please don't go away. We'll have certain or other things process within the will share with us. Sir, what is that?
Open research problems in RL security.
So he has another concept called open research problems in hardware security. So it will be nice to hear a new concept, I think. So please don't go away, and we'll take a break for 5 minutes, then we'll start. So we will continue in the same meeting. We will start now, just hold for 1 minute.
Open research problems in hardware security. So in this case, we just go through the world view of hardware security research. So basically, the classical area of security started from side channel attacks in 1988, like when Paul Walker showed the side channel attack on a smart card or a credit card or a debit card, whatever on that day. In 1998, he performed a power-based side channel attack in 1998 in the conference, the open conference, and again he cracked the key of the smart card. So this is that is where exactly the side channel attacks came into the existence. That's the starting point of hardware security in general, taken from the electronics engineer's perspective. That is, use the power consumption data, use the power traces, and get the job done. So that's the 1998. And again, the text-based attacks, the DFT-based attacks came into use in 2006. Timing-based attacks came in somewhere in 2003 to 2008. The fault-based attacks somewhere a little bit early in 2001 was reported, but much of the research was done after 2008. And EM10 laser-based instruments in 2013. So this is the basically all of the side channel attacks is we can call it as a classical area of hardware security that is started early. It is basically the hardware security means the people is to think about the hardware, the side channel attacks, side channel attacks. Side channel attacks. So the modern problems in hardware security after 2012 onwards is all about the counterfeiting at source. That is, there are two areas of counterfeiting. That is, counterfeiting at source is counterfeits coming out from the foundries. That is unlicensed with our own production, and the counterfeits coming from the test centers or outsourced test and assembly centers. Outsourced test and assembly centers. The next is the hardware trojan. The hardware trojan can be recycled parts, means we throw a lot of gadgets out of the using the maybe TV, laptop, mobile phone, and all. We throw the gadgets after which they becomes useless. Some rack picker will pick that and again will take the PCBs, remove the ICs, clean it in a river and pack it as a new and sell it as a new. These are a variety of recycling. So the malicious modifications in design, that is the generally adversary in the design house or else the third party IP, untrusted third party IP will modify the design to the malicious intentions, that is leaking the data, creating the denial of service. That is what we call it as unintentional unintentional RTL modifications and layout, RTL and fabrication. And again, the debug security, securing the JTAG, IEEE 1500, 1687. These are the areas where we need the research happen. And again, the IP security, which I already discussed the previous speakers, both active and the passive security. These are the major problems we see from the hardware security in 2012 onwards. But just to list out the problems in the hardware security for the next 1 decade is the lightweight cryptography, the new algorithms and hardware acceleration. This work was already kickstarted in 2014 or 15. We can see a lot of algorithms being proposed and implemented in hardware, and we see a lot of results in many papers, many research literature today. But still, there is a lot of scope in lightweight cryptography. Given an application, for example, I need lightweight cryptography which will be useful in testing, VLSI testing. Still, an open research area needs to be carefully addressed and carefully taken care. The next is a blockchain acceleration. It's a typo there. It's a block acceleration, but it's a blockchain acceleration. The blockchain acceleration basically needs a one-way function, especially the SHA, and a corresponding circuits and corresponding mechanisms that they call it as a NUU, the non-ounce allocation unit or something like that. So how do you implement the hardware? Means, for example, the blockchain generally implemented in the Ethereum or any other environment today is slower. If you want to make it faster, I want to use it in the hardware. How do you fastly run your blockchain systems? How do you run the blockchain systems in a very faster way? So that's where exactly the blockchain acceleration come into the picture, especially in dealing with the smart contracts and Bitcoin. Bitcoin is banned. Still, any digital currency related activity, legalize the digital currency related activity, and also the smart cities and smart contracts, which means the post-quantum cryptography and its hardware implementation. The post-quantum cryptography and its hardware implementation. This is the one area where we have to think about the quantum computers will become reality. And also there's a lot of scope for post-quantum cryptography apart from quantum. The post-quantum cryptography is where exactly we are moving away from the conventional cryptography, that is AES, RSA, and all from this conventional to we move to the lightweights like ECC and all is more conventional, more than conventional ones. And again, we move to the next area of work where exactly we need the hardware architectures and hardware implementation on this post-quantum. We need to add algorithm to architecture mapping issue, the algorithm to architecture mapping, the problems in post-quantum cryptography is still in the nascent stage. We have to find out the efficient ways of implementing post-quantum cryptographic algorithms in the hardware. That's where exactly the point is there. The next one, we just think is security in the high level. This is a very old thing. Basically, the system C is a language of 1999. Already 23 years old language in the system. But now, why the system is getting very important in now in the recent 2021, 2022, the fundamental reason why now currently the system C is getting more important. Because of the two reasons. Number one, the Verilog is a language where the floating point cannot be handled very easily. Floating point cannot be handled very easily. And again, if you implement an IEEE 1754 single precision and double precision formats also, the Verilog can handle the floating points easily without doubt. Already there are a lot of implementations to work in the manner. But the basic problem is, if you have a hardware floating point operations, and also we have a for loops. For example, a large number of for loops will come into the picture. Well, even a single for loop or for loops cannot be handled in Verilog. While few FPGA designs, especially in the ASIC design, using a for loop is prohibited in programming. So in programming, it is prohibited. The case is the basic problem is, especially in the recent algorithms, especially the machine learning and AI algorithms, we have a floating point operations and also we have a for loops coming into the picture. The fourth handling the for loops and fourth handling a floating point operations by the Verilog, it's not possible. A Verilog is an handicapped language. Verilog is an handicapped language to handle a floating point operations and for loops, but which is a bread and butter of the machine learning algorithms. But to implement the machine learning algorithms, it is better to use it to implement the machine learning algorithms in hardware. It is better to use a system C than a Verilog. That's what the notion. The purpose of that, why Verilog cannot be used for machine learning implementation? We can use it still, yes. Without doubt, we can use it and also we get a good results. But the time to market is a factor. The time to market means what is the design time? Do you take 6 months? Do you take 8 months to design a map and a machine learning algorithm into the Verilog and simulate it and test it? And you can do it in 2 months using a system C, why not? The work of 8 months can be reduced to the work of 2 months if you use a system C in the place of a Verilog to implement a machine learning algorithm. So the handicap of a Verilog, that is, handling floating point and handling for loops, can be addressed using the systems. So this is a general notion in the industry, and again the people see that, and again we see that a lot of systems algorithms are getting deployed in the real, are getting deployed in the real time. Now the system C is getting deployed, and again the people started using alien status and metal graphics catapult tools to simulate, synthesize, and model the machine learning and data learning models, deep learning models in the systems. The basic another biggest issue in the future of hardware security is the research problems are associated with the future of computing due to the end of Moore's law. This needs a lot of treatment. Basically, there are three laws which are driving the computing. The Moore's law, which we all know very well, which is now we are going towards the end of the Moore's law, or already is ended. Some people will say that Moore's law is dead, but we cannot agree on that. But the end of Moore's law is somewhat evident from 2003 itself because the power supply was not reducing. And the end of reduction in the power supply happened in 2003. After that, the power supply reduction did not happen. So that's where exactly in reality the end of Moore's law is started. But now the people agree that even the marketing people agree that in 2022 there is the end of Moore's law. There is a one part. The one is the Moore's law. The second aspect is the Dennard's law. Dennard's law deals with the low power aspect of the chip design. The power was not the biggest deal till 2006, 2007. After that, the power consumption of the chip increased so that it has reached the highest levels of rocket nozzle, and etc. If the power supply is not clamped down. Power supply is not clamped down. So the basic problem is Dennard's law has failed because the power consumption has increased drastically. We cannot have a more number of transistors because the power will increase. Dennard's law has failed. The Moore's law has failed. And the most important law, which is called as Andol's law. Andol's law has also failed. Andol's law says that the number of cores you increase, there is quad core to octa-core, the performance increment is very minimal for various reasons. So you need to get the new architectures now. This is the one part of the problem in the computing. That is, we have to address the failure of three laws at the same time. That is, Moore's law, Dennard's law, and the Andol's law. And we have to find out a new architectures. Earlier, the new architecture means reduce the channel length, reduce the channel voltage, do the voltage scaling, do the channel scaling, then get the new architecture done. You have a new processor, sell it in the market as a new high performance processor, etc. But the tree lunch is over. But you have Moore's law won't come into the help. Dennard scaling does not come into the help, and Andol's law don't come into the help. You have to find the architectural level solutions to find out the innovations to improve the performance other than nothing other than. So the case here is the next case is we have two important attacks which looks like an extensions of a side channel attacks. That is called the meltdown and spectrum. These two meltdown and spectra are so powerful attacks they can crack your hard disk data in the presence of your operating system. As around 30 researchers who worked on the meltdown and spectra attacks clearly says that none of things, either your architecture, nor your operating system, nor your hardware or software, nothing prevents you from the meltdown and spectra. The meltdown and spectra is so powerful that though there is no software solution or there is no hardware solution which will stop the meltdown and spectra. So what is the solution for this? The solution for this, redesign your microarchitecture, redesign your instructions so that in such a way that it will stop the The thing is, we were discussing. So the security problems associated with the future of computing. We last failed, as I already mentioned, and again now there is two attacks which really the lethal are meltdown and spectra. In the presence of the meltdown and spectra, no hardware and software is safe. Your hard disk is open. Anybody, if he successfully launch the meltdown or spectre attack, anybody can take any data from my hard disk. There is no stop on. Why we cannot have a concrete and a holistic security defense against the meltdown and spectre attack? The simple thing is it attacks the vulnerabilities in the instruction set of an 8086 microprocessor, or else it will attack the vulnerabilities in the instruction set of the ARM microprocessor. If the attacker is using the vulnerabilities in the instruction set of the ARM microprocessor and also an x86 microprocessor, no software virus, no operating system, nothing will stop you from getting an access to the hard disk or a secret memory or whatever is associated with it. The basic problem is that the meltdown and spectre targets the vulnerabilities of the instruction set of the microprocessor. Then what is the way out of solving the problem? How do you design your new computer? How do you design your new computer to address the meltdown and spectre? Only way you have is take RISC-V processor, open source RISC-V, then redesign your architecture instruction set in such a way that meltdown and spectre is prevented. Meltdown and spectre is prevented. Neither 886 nor MIPS nor ARM are defend against meltdown and spectre. The meltdown and spectre are two lethal attacks published in January 2018. Still, I was there here. I read this paper. I explained to my colleagues here, especially the Jagannath. And again, I understood that this is a lethal. And again, in something there is no solution for this. But the solution now the people say it is this one. Redesign your computer instructions. Redesigning of x86 and ARM is not possible. Take a RISC-V. Redesign your instruction set in such a way that the meltdown and spectre defense can be built. What are the reasons why we need to redesign our computer? One, end of Moore's law, Dennard's law, and Amdahl's law. Another one is that meltdown and spectre. So these are all. The last one is trusted computing platforms. The trusted computing platforms is an area where we already, for example, there are a lot of, already I mentioned in the last online class that there are a lot of trusted computing platforms like ARM Trust Zone, Samsung Knox, Google Work, Open Titan, etc. So these are all, what they say is they create, what are the main features of these trusted computing models? The trusted computing models are, they will just isolate the non-secure operations and secure. In secure operations, they will create a separate silo where the secure operations will occur. Then now it will shift to the non-secure operations or to some. So that the secure operation area will have an access to the secure memory, a secure part of the operating system. A total overall, it's a secure, completely a secure silo. From that secure silo, it will come back to the non-secure silo after taking all precautionary measures. This is a general component in all the trusted computing platforms like ARM Trust Zone, Intel SGX, Samsung Knox, or Google Open Titan. It's slightly different, but still the process is the technology remains same. Then the basic problem with this trusted computing modules is that are they vulnerable? Not so vulnerable. But again, it is not easy for a adversary to crack on it until unless the user gives some password or loopholes, some issue is there, something. But still, they are not recommended for the IoT systems, especially the edge nodes, because they will slow down signaling. The lead away to this implementation of ARM Trust Zone will just like it will lead away to 30 to 40% of the computing resources of the IoT edge node, where the edge nodes will become too slow and TPMs are not becomes useful. TPMs are becomes a big burden on the computing facilities of edge nodes, where exactly the TPMs does not make sense for the IoT edge nodes. The TPMs are good for my mobile. TPM, especially the ARM Trust Zone, is very good for my mobile because it is a reasonably a computing platform. But when it comes to in reality, some sensor networks collecting a data and putting an ARM Trust Zone on it is a meaningful thing. Is a meaningless thing basically. For mobile or any such kind of applications, ARM Trust Zone is good, but edge nodes like this. but not for the real industrial edge nodes or the community edge nodes. So there exactly the trusted computing modules needs to be replaced by something else. What is that we will see. The next is the security design of the future IoT edge nodes power supply. The people simply failed that the power supplies are vulnerable. If you destroy power supply, everything can be addressed. But at the same time, they don't want to destroy the power supply fully. They tamper with the power supply, and again they ensure that power supply they will have a control. When they will switch on, they will switch off. They will have a remote control of the power supply of my. So they are not touching my system. They are not touching my system. They are creating a denial of service or similar kind of attack by playing with the power supply. So this type of attacks on the edge, IoT edge nodes is also has been reported in the research. So these are all the hardware security for the next decade. That is, if I briefly recap it, lightweight cryptography already started 10 years back, and again still there is a lot of scope for building new algorithms and mapping the algorithms to the accelerators. Blockchain acceleration, post-quantum cryptography and its hardware implementation. High-level languages like SystemC, which I already mentioned, why people use SystemC in place of a Verilog because of the handicap features of a Verilog like landing, floating point, and for loops. Security problems associated with the future of computing, just I mentioned. TCPs, the problem TCPs are good but not suitable for IoT edge nodes. Finally, the power supply problem. So the next step is I will take one problem. I will take out of this. I will take a trusted computing platforms. I will go deep into it, but that is called as a DICE. Now, if it is trusted computing platforms are not feasible for the IoT edge nodes, so 8-bit microcontroller or 8-bit microcontroller. What is the solution? The solution is something called as a DICE. It is called as the device identifier composition engine. This device identifier computing composition engine is a replacement for the DICE. Sorry, replacement for a DICE is a replacement for the trusted computing platforms, where it takes very less amount of computing resources when compared to that ARM Trustzone, where it creates a separate silo of secure execution environment, etc., or trusted execution environment, etc. Vulnerabilities in modern computing, communications, and control systems allow cyber attackers to increasingly sophisticated and relentless their efforts, because that is a way where we need a trust zone, secure environment, etc. But these solutions to the are challenging power, security, resource, and other constraints. So this one, while the systems, the TPM, that is trusted compute platform modules, have many practical and flexible security benefits. The TPM is not feasible for most of the IoT space like microcontroller units and system on chips. ARM components in more complex peripherals like advanced driver assistance systems. For this reason, based on the trust platform architecture hardware requirements, the device identifier composition engine draft spec, the working group is exploring a new security and privacy technique. This is a TCG group, Trusted Computing Group. This is a IEEE group, which already they have published this documents on DICE. Now, academics and industry has to experiment with DICE architecture and say that whether it works or not. So this is the goal of a DICE. The goal of a device identifier composition engine is to develop a new approaches to enhancing security and privacy with a minimal silicon requirements. Every simple computing capabilities combined with the software techniques can establish cryptographically strong device identity as software and security policy and enable safe deployment and verification software updates. These are all valuable security enhancing capabilities that can be done using the DICE. So we can see the DICE diagram on the slide. The power on, the unique device secret, a number, and we call it as a chip DNA, or some unique number generated by the TRNG or the physical controllable, which you have discussed in the last few classes. There can be a number here. That number will use, I will create a layers of security. Secret 0, secret 1, secret 3, secret 1. DICE works by breaking up the boot into the layers and creating secrets unique to each layer and configuration based on the unique device secret. Unique device secret. If the different code of or configuration is booted, at any point in the chain, the secrets will be different. Each software layer keeps the secret it's completely confidential to use. So this is how exactly that dice will work. This is basically the dice feature. If you look at this dice feature, we have a UDS, that is a unique device identifier. There is a unique device identifier. After a unique device identifier, I have here the alias key generated. Then go to the second stage of the code. Here the same UDS will create a device ID determines to specific ID. Then again it will create a device certificate to the next one. These are just a one-way functions. These are just a one-way functions like a HMAP or SH. HMAP or SH. These both the certificate generation are just a HMAP functions. Based on this HMAP function, the next layer will be done, next layer will be done, next layer will be done. But the advantage of this is that any intrusion will need to take a certificate from here. So that a different certificate is available, then that is the update or intrusion is discarded. So this is how exactly this dice will work in the place of a trusted computing model. Trusted computing model. If the dice is the root of the trust of measurement, since its misbehavior cannot be detected, it must be inherently trusted. The architecture of dice unconditionally generating the correct CDN for layer 0 and layer 0 being then linked to the next link to the next chain of trust. The dice establishes the device booted the first mutable code provided by the manufacturer, that is UDS 0. Generally, we generate the UDS 0 with puff or with the RNG. This element detects the persistent modification of layer 0 and comparatively, the use cases places few requirements on device firmware of the operation of the dice. So this is a simple equation, one-way function, maybe HMAP or it will be a SHA. So this is a sample of Microsoft implementation, but here they use three areas, means they create a dice code, a unique in the system on chip, right? And this is the chip basically. This is a chip. On the chip, we will have a dice engine, and above that, they will create a firmware layer. Above that, they will create a firmware layer. But the idea is, why we need a dice engine? But we can build the certification and all into the firmware level itself. That's where exactly the work is going on in this. But as of now, most of the works, right? Most of the work, whatever we are calling, right? In this case, this is a hardware. This is a UDS is an hardware. Dice engine is an hardware. It's inside a sock. About the dice core is basically a firmware with a lot of APIs getting access to it. But the case here is the original dice is something like this. The original dice is something like this. Here they don't say that whether you implement this device ID asymmetric key generation in hardware or firmware. But every hardware, every guy has done it in the firmware level. But this is not in spec with UEF. There is something called as a unified extendable firmware interface is a one Intel standard is there. Whether this dice is in alias with the UEFI, nobody has tested it. It's a open research problem. Because from my laptop to my mobile to my any other device today conforms to the UEFI standard. That is a unified extendable firmware interface, UEFI standard. This UEFI standard conformity of a dice is a one question mark. After that, whether to implement, now most of the people will implement this alias key and device ID generation from the puff. They will get a puff here, the key is there from the puff. They will generate the all other stuff in the case of this alias key in the firmware. But whether that can be done in an hardware, can we make it as a separate dice code in conformance with UEFI is a open research. Means I'm just taking a one problem that which I have listed in the case of what are the modern problems in next decade. I have just taken a one TCP problem, trusted computing problem. In trusted computing problem, there are many problems out there, like creating an infrastructure IP, creating an hardware defense, creating a software defense, creating a platform for the digital twins, the TPMs. Like that, hundreds of problems are there. Just I have taken a one problem where for IoT edge nodes, the TPMs are very huge, bulky. So the dice is the solution. If the dice is the solution, there are problems. One, whether the dice hardware is hardware, UDS is hardware. About that, now everybody implements it in software or firmware. not exactly software, it's a firmware. Can you then implement that in the hardware itself and make it compliant to the UEFI? How do you do that? What are the problems? It's basically at least 2 to 3 transactions, IEEE transactions. 2 to 3 IEEE transaction work is working on dice and making it UEFI compliant and implementing in the hardware along with the RISC-V process. So it's a secure boot component, a security boot component may have a dice, may have a UEFI compliant, and then it becomes a secure boot core. That secure boot core will be a IEEE transaction. How do you design it and how do you verify it, how do you validate it? So like this, we can list out the several problems, several tens of problems are there in the each area which we have discussed. So this is one way of this Microsoft Dice implementation. Again, it is this particular section is implemented in firmware. Above that, there is a boot firmware. This is actually as a part of a BSP, the firmware security descriptor, something like that. They will say this. Firmware security descriptor or something like this. They will say that. Yes, everything is this is above is a firmware understanding. So what are the dice users? Dice users either you can use HMAC or hash functions or any other lightweight one-way function can be used. See, it's a low-hanging fruit in the research. Don't know, but to my common sense, yes. The dice is a low-hanging fruit in the hardware security research. Yes and no. Hardware implementation of dice fully in hardware and its performance is still open research problem. Either it's FPGA-based design or a RISC-V based assessment, or it's any other type of assessment is still an open research problem. It's a low-hanging fruit. Somebody can try it out. Thank you.
If any question, you can ask from online.
Hello.
Yeah.
Hello.
Pratik, you can tell.
Yes, sir. Regarding a schematic of cryptography of random number generation in true and pseudo sense, this model of hardware security, how is the sir limitations of that in TRNG sense? If FPGA prototype will be used for that, basically limitations which you tell. Today you describes how is the limitations and what is the limitations and future scope about that topic. In terms of hardware security in cryptography in AES 32 as well as other cryptography sense encryption and decryption procedure.
Fine, if I understood your question properly, the first question is on TRNG, the efficiency of TRNG, whether we are using means to generate the UDS, especially in the case of a dice, we need a unique device number or unique design identifier, something like that. The UDS, today the number, the unique secret, the unique number generation is required for every chip. For every chip getting manufactured needs to have a unique ID. That's what the industry feels also. Either they will employ TRNG or PUF in that direction. PUF is a more stable option for various reasons. And TRNG is a very viable option because of the hardware and its corresponding management related issues, especially the logistics issues when it compared to the PUF. PUF needs a lot of logistics. We have to give a CRPs, collect the CRPs, store the CRPs, and manage the data, map the chips and the CRPs. All these jobs all this work is there with the PUF. But in the case of the TRNG, this business is not there. Run the TRNG, just store the unique value into the OTP directly when chip is under testing or under production, the job is done. But the TRNG has a less logistics when compared to the PUF. But PUF has an advantage if further a PUF-based IoT system, a PUF-based any other system can be built. That is where exactly the PUF has got its own. But in the case of the TRNG, the quality and efficiency of a TRNG needs to be determined by the NIST standards. As already mentioned in last class, that is NIST standards and the statistical properties of a TRNG output needs to be assessed. Whether it is an FPGA or ASIC, it's the same thing. It has to go through the NIST standards and potency tests. I hope I answered your question. And the second part
Hello.
is
Yes, sir.
AES.
Hello. Yeah.
AES.
A novel approach of proposed TRNG generation. Then how is the basically 64-bit post processor generation? Then basically how is the some parameter like latency and throughput and other parameter comparison of any cryptographic sense parameters like NIST test suite statistical property FIPS test suite. So how is the model will be correlated with about in terms of limitations as well as proposed techniques, which will be the main and core proposed procedure will be used for that proposed work in sense in hardware security terms.
If I answer your correct question properly, applications of TR, for example, barring of the NIST and statistical test, there can be some other tests like throughput, speed, latency of a TRNG. That if that is the case, see, the question is better use the puff in such cases because the TRNG latency completely depends upon the environmental and temperature variations, where generally we don't have a control on it, and also we have a TRNG throughput, right? How much throughput? If the length of the TRNG increases, for example, if you increase the pseudorandom number generator more than that specific length, that is more than 16 or 24 or something like that, it becomes vulnerable. It is easy to attack them. Again, you don't get the pure very good random numbers. A unique random numbers generation is very difficult after 32 numbers, to the best of my knowledge. It becomes vulnerable basically. And again, you cannot design a TRNG of such a length inside the chip today. With the implementation is also a big problem. If it is more than 32-bit TRNG inside the modern chips today, because it takes a lengthily too much, means it's somewhat more complicated stuff. Better if you have a requirement of latency, deterministic latency, and if you want to build a proper unique number generation scheme, better you use the physical unclonable functions than the TRNG. If you are fixed to the TRNG, better you fix it to the maximum 32-bit or 64-bit TRNG, not more than that. If that is the case, you ensure that what is the latency completely depends upon more than the latency and other things, the statistical text are the matter. If you play with the latency of a TRNG, you will be compromised on your quality of the statistical test. But I prefer a better statistical results than the latency of a TRNG.
Sir, approximate entropy in terms of temperature will be calculated. This hardware security in statistical 15 statistical NIST test parameters in terms of output random data bits calculations.
Fine. Fine. Okay. Means the thing is that if you have done statistical tests, it's good. Publish it. And publish your novel design and its results.
Sir, CMOS inverter CMOS simulation use this procedure which you tell today to, for hardware security with random number generation.
Anything needs to pass through the same test.
Okay.
Any other question? I think somebody from audience was asking.
Hello, sir.
Yeah.
Sir, regarding how is the SOC designs calculation for bit stream generation, this procedure hardware security, which you tell today? How it is the possible, sir, procedure?
I think, may I know what you are asking? Means you want to create SOC for the hardware security, what process Vidindra has suggested?
Yes. Not as how is the sir, procedure of SOC designs today with if I design with the SOC design, then how is the procedure and methodology I'm asking?
So I think it is the same now, like VLSI design flow. Okay, that only, but at the end when SOC means there will be a system. So if you are only targeting a particular component like cryptography algorithm, so you may not tell that it is a complete SOC. So if you are like you are having a TRNG module, then you can pass it through like first C or MATLAB, then RTL, then synthesis, then gate level, then place and route. Then you can generate IC or ASIC out of that. For SOC, it has to be with a processor and a complete system. Are you getting? Yeah, any other queries you are having?
Sure. Yes, sir. Yes.
Yeah, so
How
for that,
this model will be feasibility. I am asking to the of energy efficiency and feasibility parameter. How is the observed result is feasible after calculation of hardware results? Lookup tables and area, power consumption, bit rate, and other parameters like a product entropy, approximate entropy. So for other calculation of this parameter, how is the model will be appropriate in terms of limitations? I'm asking to that, sir.
so you are telling like what process Vidindra shows on that, or you are telling about TRNG?
Okay, means if it is a TRNG.
Today, sir tells. I am asking, sir. Sir, discuss the model.
Our model, your model, sir.
Today I discussed about only the UDI,
Uh,
where you can get the unique number either from the puff or TRNG, which is suitable. One, take the best TRNG, best puff for your given design, for your given constraint and for a given requirement. That's it. So how exactly you will define the quality of a TRNG? Generally, the industry will go by the NIST standards. The rest is left to the better TRNG, designing better TRNG is again another one big research problem, whether you will start from the transistor level or whether you will start from a standard cell level itself, or else whether you will do on the FPGA based TRNG number generation if required, if the research requires. It depends on how do you mean the methods to follow to generate the quality TRNG devices. On FPGA is quite different and ASIC is quite different. So if it is an ASIC case, obviously somebody has to start with the transistor level, designing inverters and getting the job done. High quality TRNGs can be done at the ASIC level from the full custom layout only. Not possible in this other standard cell level. But when it comes to the FPGAs, we have to understand the FPGA architecture clearly. We have to go through the library clearly, libraries of the cell libraries clearly. Then we have to choose an appropriate cells and try with the manual layout and all. Manual placement and routing we have to do clearly on the FPGA, the floor planner. Then we have to ensure that whatever we are doing is correct. Our calculations, our design intentions, and our floor planning matches. Then we have to calculate the TRNG by varying the temperature and all. The question will come out, you vary the temperature in the room in the lab. For example, if I have a 27 degree, 30 degree, or 35 degree lab temperature, we am collecting the TRNG. But I want to collect the TRNG data for the 80 degree temperature or 90 degree temperature. How do you collect it? The question will come. Then just go to the home and get the air dryer. Then apply the air dryer on the chip for 10 minutes and ensure the temperature is above 80 degree and collect the TRNG. Then TRNG should vary because there is a drastic difference, right? 30 degree to 90 degree or 80 degree. In air dryer, you can vary. Means it's very easy if you find out a ways like this. 30 degree, what is the TRNG output? 40 degree, what is the TRNG output? Because you are varying the temperature. The air dryer is a simple example. Or else if you want to test other environmental parameters, for example, there is an external radiation. How do you do the external radiation? Go to the paint shop, Berger paint shop, take a small uranium powder, then apply on your FPGA and again leave it for a day and again check your TRNG. You just see what is the gamma effect radiation on your TRNG, how it is working. Not only TRNG, any circuit functionality and FPGA implementation can be tested for the minor radiation effects. So the temperature, don't break the head. Go get your sister's hair dryer and test the TRNG parameter in real time for FPGA, whether it works or not.
Hello, sir. Sir, how is design TRNG is integrated in a fabricated chip or not? How is the characterized? This parameter, this model, using this model.
It will be the same thing. Collect the output, and again apply this thermal streams and collect the data. Means after collecting data, you have to apply the NIST test on it and again ensure that it's working. What are the parameters? The assessment of output of TRNG does not differ much between ASIC and FPGA.
Okay, sir.
Any other question? We are towards the end of this session.
TRNG will help to generate a private key or public key.
There's a lot of considerations here. Noise-based TRNG. Lot of TRNGs. I showed it on the last.
If you want to generate a public key and private key, then how we can generate this or blockchain?
The key generation mechanism, cryptographic key generation mechanisms. As of now, they are the suitable because they are all trusted. So you look at the conventional key generation schemes are there. The cryptographic book we will get right. As of now, they are still using it. Using puff, then use the puff key, then generate the cryptographic key is the one possible. Puff use karo, और puff CRP से you generate a cryptographic key for blockchain. Don't directly use the puff output as an input to the cryptographic blockchain because of various reasons. But as of today, most of the industry does not use puff for blockchain. They use the normal conventional key generation schemes.
Okay. We are at the end of this session and we thank Professor Sudhindra with us and so once valuable time he has traveled here and he is here with us for 2 days. So anybody wants to interact, they can also do that. And thank you.
Thank you, sir. Thanks for the invitation.
Okay, thank you.
It's always pleasure for coming back to this. And again, I made a lot of friends like you, soulmates like you.
So we have started actually from VLSI lab of NITrourkela. And we said that under the guidance of Ekima Professor and another 2 servers there, they were not here. So anyway, now
Always thanks for the invitation.
carry forward and do certain research work which will help our research only.
Thank you. Thank you, sir.
Thank you so much.
Okay, tomorrow we'll have a application example for agriculture of IoT. For IoT, it is by Professor Debanjan Das, I already told. So please join us at 9:30. And I think you have to do a MCQ test also, second MCQ test. So that timing and all I will mail, and that we'll do online in Google Form again. And second half we'll have Professor BD Sausar with us, so he will tell about edge computing, cloud for IoT, etc. Then we'll have valedictory session towards the end. So I am actually very busy. So to conduct all these sessions and its things. So anyway, I will. We have already created. So I will send the attendance link. You please fill for individual day or each session, and which will facilitate us to generate certificate for all as per the rule. Okay. Thank you for today. We'll meet tomorrow again. Thank you.